Hello, welcome to the second tutorial on Laplace transform. So in our first tutorial we did find the Laplace transform of single functions, something like Laplace of f of t and the rest. So if you are new to my channel or if you haven't subscribed to my channel, kindly subscribe for more videos. So today's video we will look at when you have a function f of t multiplied by another function e to the power at like we have here. Okay. Alright, so if I have this, how do I find the Laplace transform? Okay, the formula is there, but let's try to prove it and see. Okay, so if you can remember, the Laplace definition was given as this: Laplace of f of t is equal to integral from 0 to infinity f of t times e to the power negative st dt. Now with this, we said that the s here is a constant, okay, with respect to the t, meaning that after the integration, after finding the Laplace, every answer that we'll get will be in terms of what? S. Okay, so let's look at a situation whereby we have this to be for us to find the Laplace. Okay, so the Laplace of e to the power at then f of t is equal to, using the definition, this becomes e to the power at f of t e to the negative st dt, right? So now the whole of this will be equal to integral from 0 to infinity, then e to the f of t times e to the negative st plus at dt due to the product of this e and this e. Okay, now everything will give us integral from, let me write it again. Okay, integral from 0 to infinity f of t e to the, I'm factoring negative s minus a out, then times t dt. Okay, so this is what we will get. Alright, now we said that Laplace of this will give us what? Capital F of what? S, as in a function that will be in terms of only s, this term that is attached to the t. Okay, so the term here that's attached to the t is always what we will get. Okay, if that is the case, then let's look at a situation whereby the term attached to the t is what? S minus a. Okay, so with what we have here, okay, with this one, now we've gotten something like Laplace of the whole of this. Okay, let me write it. Okay, Laplace of e to the at f of t, okay, is equal to integral from 0 to infinity of f of t e to the negative of s minus a t dt. Okay, now when we're having Laplace of only t, f of t, the final answer was what? F of s, meaning we just find the Laplace of f of t, then the variable that we get will be in terms of what? S. So here, considering this side, you can see that the old one, the general definition, was having minus, only minus s here. Here we have minus s minus a, minus of the expression s minus a rather. Okay, so it means that the whole of this Laplace will give us capital F of what? S minus a. If you could see, this was capital F of s and this s was here. Okay, it's here. Then this one too, it will be capital F of this s minus a. Okay, it's the same form of Laplace definition, just that this time the constant here is what? S minus a. Okay, what this f of s minus a means is that if you have e to the power at times this, like we given here, Then the first step we should do, okay, we will have to compare the question to this one, okay, and find our f of t. So after finding our f of t, what we do is, given a function like this or a question like this, find or determine your f of t in it. Then the first thing you should do is find your Laplace of f of t. Okay, it will give you capital F of s. Okay, then the Laplace of e to the power at times f of t will simply be equal to, knowing your a here, okay, then from this function that you find, wherever you see s, you put s minus a. Okay, so very simple, right? Let's take one example and you would understand. Okay, all right, so we have an example here. Let's find the Laplace of e to the power 2t times sine of 2t. Okay, so here comparing this that we have here with this one, okay, comparing the two, you can see that f of t is what's equal to sine of 2t. So our first step is to find the Laplace of this. Okay, now we did the Laplace of sine of at, and we said Laplace of sine at is equal to a over s squared plus a squared. Okay, this means that the Laplace of sine of 2t would actually give us, let me cut this off, will actually give us, a is what, comparing this to the general one, a is 2, then you have s squared plus 2 squared, which is 4. Okay, so we just, after finding the Laplace of our f of t, we determine our a from this same question given. Okay, so comparing this one and this one, you see that e to the power at is here, this side, and here is e to the power 2t. So our a will be what's equal to 2. Now, knowing this, we said this is equal to our capital F of s. Okay, so to find the Laplace of the whole of e to the power 2t times sine 2t, what you do is, after finding this, we find capital F of what, s minus 2. Okay, because our a is 2, we find f of s minus 2. So let's quickly erase it and find it. Okay, so we said the Laplace of f of t, which was sine of 2t, actually gave us 2 over s squared plus 2 squared, which is 4. Okay, so let me erase it and write it straight. Okay, so s squared plus 4. Okay, now this means that our main question, which is the Laplace of e to the power 2t sine of 2t, is actually equal to, we said that we find our f of what, s minus a, where our a is what, 2. Okay, so our a equals 2, then we have f of s minus 2. That is what we are coming to find. So wherever you see s in this, we put s minus 2 there. Okay, so it becomes s minus 2 squared plus 4. Okay, so this becomes our final solution or answer to this question. Okay, so let's look at another situation whereby the 10 multiplying f of t is not just e to the power 80 but something else. Okay, so alright, so let's look at a situation whereby we have Laplace of t to the power n times f of t. Okay, okay, so we have Laplace of t to the power n times f of t. How do we go about it? Okay, so this is how we do this. I'll quote the general formula straight and we'll prove it in another video. Okay, we'll take our time and prove it. Okay, so if you have this, what you do is first find your f of t, Now after finding your f of t, the second step you do is you find the Laplace of f of t. Okay, after finding the Laplace, it will give you what? Capital F of s. What this capital F of s means is that it will give you a function in terms of s. Okay, now you identify your n, okay, being it 1, 2, 3, or whatever you want. Okay, then the last one, what you do is you find the nth derivative of your capital F of s with respect to s. Okay, then the last one you do is multiply -1 to the power n of the nth derivative of your capital F of s. Okay, so first just call one of the functions, or make sure that you identify your f of t. Okay, then after that, what you do is find Laplace of f of t, then know the power of t. Okay, in this question. Okay, so t to the power n, it can be t to the power 2, 3, 4, whatever you want. Okay, then what you do is, the next step is differentiate your f of s with respect to the n, the power of t. Okay, then you keep it like that. Then the last thing is multiply -1 to the power n to the solution you will get after the differential. Okay, so now let's take an example and go through it. Okay, alright, so we have an example like this. Find the Laplace of t times sine of, or let me use cos. Okay, cos of 2t. Alright, so with this, what you did was identify your f of t in the question given, and that will be what? Cos of 2t, comparing it to this one. Okay, now you know that t is with the power of what? 1. That is why we have just t, so our n is what? 1. Okay, so what you do is find the Laplace of f of t, which is cos of 2t, and we said the Laplace of cos at. Okay, we have cos at, f of t equals cos at, then Laplace of f of t, if you remember in our first video, we said is equal to s over s squared plus a squared. Okay, so very simple, right? So I hope you can remember this. Let me clean it. Okay, so it's s over s squared plus a squared. So here we just come to this thing, f of t, and that is cos 2t, so it becomes s over s squared plus 2 squared, which is 4. Okay, that is our what? Capital F of s. Now the next step is differentiate your f of s with respect to the n number. Okay, so we have n to be 1, so you have to find the first derivative of f of s. Okay, if n was supposed to be, let's say, 2, we'll have to differentiate f of s 2 times. So now add the ds of f of s, which is what? S over s squared plus 4, will be equal to what? So using the quotient rule, you first say that you differentiate the top one first and you get 1, then multiply by the denominator, that is s squared plus 4, then minus the top one times the derivative of the denominator, which is 2s. Okay, and that will all over, you have s squared plus 4 all square. Okay, now this will be equal to, if I have s squared times s squared plus 4 times 1, it becomes just s squared plus 4. Okay, you let me expand it and you understand. Well, s squared plus 4 minus 2s squared. Okay, all over s squared plus 4 all square. Now the whole of this will give us what? S squared minus 2s squared. So I get what? 4 minus s squared. Okay, then the whole of this over s squared plus 4 all squared. Okay, so this is what we have. This is the numerator, that's 4 minus s squared over the denominator, which is this. Okay, so now let's write it properly and look at the next step. Okay, so we said this is equal to 4 minus s squared all over s squared plus 4 all squared. Okay, so now the next step is we multiply -1 to the power our n, and n is 1. Okay, so we multiply -1 to the power n by the derivative that we had, that is 4 minus s squared all over s squared plus 4 this squared. Okay, and the whole of this will be equal to -1 will go through and get s squared minus 4 over s squared plus 4 all squared. Okay, so this is the final answer. So whenever you have a t to the power n times f of t, then you use this format. Okay, alright, let's look at the last situation and we'll solve a general question, and that will be it for this lesson. Okay, alright, so what if you have a situation whereby you have something like this: Laplace of f of t over t. And how do we go about this? Okay, so Laplace of f of t over t. Alright, so this one, with this, what you do is you first make sure that you find the limits of your whole expression f of t over t, okay, as t approaches 0, and if this limit exists, okay, if it exists, then you continue with the second one, then you find the Laplace of only f of t, and that will give you what? F of s. Okay, then the last one is the solution to this whole problem is equal to the integral from 0 to infinity of this capital F of s ds. Okay, so here you apply your basic ideas in integration, and also you use the improper integrals. Okay, alright, so let's get into this and solve one example, and then we'll be done for this lesson. Okay, alright, so let's solve this. Find the Laplace of sine of at over t. Okay, so how do you find the Laplace of this? Alright, we said the first thing, find the limits as t approaches 0 of the whole expression given to me, which is sine at over t. And with this, if I put 0 in, I'll get 0 over 0, which is what? Indeterminate. So what we use is we use L'Hopital's rule. Okay, so then this whole thing is equal to limits as t approaches 0 of the differential of the top one. That will give us what? A. Is it A? Yes, A cos of at all over 1. Okay, and this will give us, putting 0 in, we get, cos 0 is what? 0, so all we'll be left with will be, so cos 0 is 1, so it will be A times 1 over 1, which will give us what? A. So this limit is true and it exists, right? So once it exists, what we do is find the Laplace of f of t. And now our f of t will be what's corresponding to the question is what sine of at. Laplace of sine at is equal to what? A over s squared plus a squared. Okay, so now this is our what? Capital F of s. So with this, let's clean everything and do the integration. I think that the whole of this Laplace will be equal to the integral from 0 to infinity. Now f of s is what? A over s squared plus a squared ds. Okay, so this is what you are coming to work with. Wow, it's pretty this work is really plenty, but then we'll do. Okay, so what we are coming to do is we are coming to integrate from 0 to infinity a over s squared plus a squared, okay, ds. And from our idea in improper integrals, we said that we just have to integrate only this side, then after that we replace infinity by a certain variable, let's say n. Okay, then after everything we'll find the limits of the whole computation as n approaches infinity. Okay, so let's first try to integrate this side. Okay, now with this integral we can't just do a normal integration. Okay, so what we're gonna do is we're gonna go somewhere to trigonometric substitution, integration of polynomial functions using trigonometric substitution. Okay, so what you do is from the trigonometry, the basic idea we know is cos squared theta plus sine squared theta is always equal to 1. Okay, so now if I choose to divide the whole of this thing, the whole of this by, let's say, sine of theta or cos of theta, something will be changed here. Okay, so let's try to divide the whole of this equation by cos squared theta. Okay, if we divide this side by cos squared theta, this side by cos squared theta, and this over cos squared theta. Okay, you are dividing through by cos squared theta, we get something like 1 plus what? Tan of theta. Okay, so when you divide this by that, we get tan. Okay, so you get tan squared theta. Okay, because 1 over cos theta or cosec cos squared theta is the same as cosec cosec squared theta. Okay, so CSC squared theta, and so this is what we have. Okay, so let me interchange the tan and the 1. Tan squared theta plus 1 is the same as 1 squared. Okay, and this is equal to cosec squared theta. Okay, so what we are coming to do here is that looking at s squared plus a squared, this looks pretty much like the tan squared plus 1 squared, because in the s squared plus a squared, the variable is in terms of s and a is a constant. Here too, the variable is in terms of theta and 1 is a constant. Okay, so what you can do is that you want to make sure that we manipulate this s squared plus a squared so that we get something like something squared plus 1 squared. Okay, what we can do is just factor a squared out, and this is why we have s squared over a squared plus 1. Now if you multiply a squared through this, you get this back. Okay, so let's try to, I'm just showing you this in case you've forgotten. Okay, all right, so a squared out. Okay, then we have x over a. From indices this can happen. Okay, plus 1. all right, so this is what we've gotten. Okay, so comparing this one and the tan, you could see that there's a s over a squared here plus 1 all squared. Okay, so if we can do this, if this is possible in this bracket, okay, if that is the case, then we can simply represent s over a simply by what? Tan squared theta or tan theta. Okay, all right, so let's put in mind and represent or replace s over a by tan theta. Okay, so what you have to do is that we are saying that we let s over a equals tan theta. Okay, if that is the case, then s is equal to what? A tan theta. Okay, then the s the theta. Okay, the s the theta would actually be equal to what? When you differentiate tan theta, you get sec squared theta. Okay, so you get a sec squared theta. Okay, now this means that the s is equal to a sec squared theta the theta, but let me write it well. Okay, I'm coming to write it somewhere so that you can see clearly. Okay, all right, so the s will simply be equal to a sec squared theta. The square doesn't want to come. Okay, a sec squared theta the theta. Okay, now let's try to replace it back and see. I hope you can keep these in mind. So very sorry for that, because if you could remember, I said something like tan squared theta plus 1 squared, that is 1, equals cosec. Actually 1 over cos is sec. Okay, so sorry for the first one, sec squared theta, and we said that our denominator became a squared out s over a all squared plus 1, and we let our s over a be equal to tan theta, and with that we said our ds was equal to a sec squared theta d theta. Okay, so now what you do is, in this integral we just replace things as they are. Okay, so everything will become integral from 0 to infinity, then a over, firstly it changed to a squared out, then s over a all squared plus 1 ds, right? And everything changed to 1a can cancel this, so we'll get integral from 0 to infinity, then 1 over a out, s over a was tan theta, so it's s over a squared, so if I square it becomes tan squared theta plus 1. Okay, then the s now becomes a sec squared theta d theta. Okay, now things are getting clearer here. The whole of this will give us what? Let me clean this. Now the whole of this will actually give us what? looking at the situation now, this a can take this a out, and 1 tan square theta plus 1 is equal to what? Sec square theta. So the whole of this is the same as this one, and this can take this out. So actually it's like we've been able to cancel everything, and everything has now become integral from 0 to infinity. We are just we are just maintaining the limit. We won't change it because we will change the variables back to s. Okay, so you get 1 d theta. So everything here has now been simplified as this. Okay, so let's clean everything and find the integral and go. Okay, and this will give us what? Actually the limit was this. This will give us theta, then the limit is 0 to infinity. Okay, now with this here, if s over a is equal to tan theta, then theta will be what? Theta will actually be equal to what? Theta is equal to what? Tan inverse of what? The fraction s over a. Okay, so now our whole idea or our whole integral becomes tan inverse of or arctan s over a, then the limit of integral is this. Okay, so now this is where our improper integral comes in. Okay, so he says that with the improper integral, what we do is we replace our infinity by n, and so we'll just find the limits as n approaches infinity of just putting 0 and n in. Okay, so here our infinity here will change towards n. Okay, so it becomes, when I put n in, it becomes what? Tan inverse of n over a minus tan inverse 0 over a. Sorry. So with the limit of integration, it is actually from s to infinity, not 0 to infinity. Okay, kindly forgive me. Okay, so it's from s to infinity. Okay, so here will be tan inverse of n over a, then here will be s over a. Okay, so that is it. I'm really sorry. Okay, so it's from s to infinity. Okay, so with this, what are we going to get? We're going to get something like tan inverse of n over a is the same as tan inverse of infinity. Okay, because as n approaches infinity, so we have the limit as n approaches infinity. So the limit of as n approaches infinity, I just put infinity in place of n, that is this side, then we get infinity over a, and that will still give us infinity. Okay, so we get tan inverse of infinity, this whole limit will give us this, then minus tan inverse of s over a. Okay, so let me erase some parts. Okay, so if you could remember, tan of pi on 2, that is tan of 90 degrees, is actually infinity. Okay, so it means that tan inverse of infinity will give us what? Pi on 2. Okay, then minus tan inverse of s over 2. So the Laplace of sine at, so it's s over a rather. Okay, sine at over t is actually this answer. Okay, so pi on 2 minus tan inverse of s over a, or you can also say that this is 90 minus pi tan inverse of s over a. So tan is actually in relation with cot. Okay, so they are just separated by 90 degrees, that is pi on 2. Okay, so if I get 90 degrees minus tan, I'll get cot, and cot 90 degrees minus cot will also give me, what do you call it, tan. Okay, so it means that pi on 0 is 90 degrees minus tan inverse of s over a will actually can also give me this cot inverse of s over a. Okay, so if you see this in some books, they are right. Okay, like I said, kindly forgive me, the limit of integration is actually supposed to be s to infinity capital F of s ds. Okay, so this is what you always do. First, we said that test if this this whole of this expression, the limit as t approaches 0 exists. If it exists, then you go ahead and find the Laplace of this f of t. Okay, the f of t in the expression, and after finding the Laplace of f of t, what you do is you come and find the integral as s moves from s to infinity, okay, of f of s ds. Okay, all right, so thank you, and don't forget to subscribe to my channel if you haven't subscribed. Okay, see you next time.